Alright, so this is Mr. Walker again, and we're moving into topic 2.9, logarithmic expressions. And to start out, every operation has one inverse operation. And if you think back to your early algebra classes, for instance, if I were to add 3, I know that the inverse is subtracting 3. If I were to subtract 4, I know that the opposite is to add 4. And that's how I solve equations. Or if I had x divided by 5 equals 15, I have to do the opposite of dividing by 5, which is multiplying both sides by 5, doing the opposite. Or if I had this equation, I have to do the opposite of multiplying by 5, which is dividing by 5. So in algebra, we're always doing the opposite. That's really important to keep in mind as we look at logarithmic expressions and exactly what we're doing here. So continuing this discussion on the inverse, let's look at some of these. Operations. Addition. The opposite of adding is subtracting. So over here, go ahead and put subtraction. That's the opposite of adding. And if I wanted to solve this, I would do the opposite of adding 3, which is subtracting 3 from both sides. So I have to do the opposite to actually solve the equation. And look right here, multiplication. Here's multiplication. 3 times x equals 7. To get rid of that 3, I have to do the opposite. The opposite of multiplying by 3 is dividing by 3. So I divide both sides by 3. And I can solve that equation. So the opposite of multiplication is division. Cubing. So here I have the x, and it's been cubed, and that equals 7. And I want to solve for the x, so I have to do the opposite of cubing. Well, the opposite of cubing is the cube root. So I'd have to take the cube root of both sides. The cube root cancels out the cube, so that gives me x. You're always doing the opposite to solve equations. So the opposite of cubing is cube root. But let's look at this. Exponentiation. This is where you have a number being brought to a power where the power has an x in it. And we saw that going back a few lessons ago. Whenever you have this, that's an exponential equation. And we're just multiplying by 3 over and over and over again. Okay, so whenever you have the x in the exponent, that is called exponentiation. But I still want to solve this. I want to get the x by itself, just like I want to get the x by itself in all these. To get the x by itself in all these, I had to do the opposite. Well, it's no different here. To get this x by itself, I have to do the opposite. But then the question is, well, what's the opposite of exponentiation? It just so happens that the opposite of an exponential is a logarithm. The opposite of an exponential is a logarithm. So if I want to get this x by itself, I have to do the opposite, which again is a logarithm. So let me show you how that's going to work. And you can actually put that right here. Has a question mark. The opposite of exponentiation, logarithm. Okay, so we're going to be using a logarithm to solve these. And I'm just going to pull this one out and kind of show you how it works. The notes kind of skip over this, and they don't really explain what's going on here. So 3 to the x equals 7. 3 to the x equals 7. Let me give myself a little bit more room to write. 3 to the x equals 7. Now I want to get this x by itself. So I have to do the opposite of an exponential, which is a logarithm. So I need to take the log of both sides. I've got to do the opposite of an exponential. I have to take the log of both sides. And when you're doing a logarithm, there's actually a number down here. I'm going to write a number down here. This is called the base of the logarithm. And this number that goes right there needs to be the same number that's being raised to the power. So it's going to be a log base 3 of 3 to the x. But I have to do the same thing to both sides. So this also is a log base 3. Okay? So I did the opposite. The opposite of 3 being raised to the x is log base 3. And I do that to both sides. Now what happens is this log base 3 cancels out this 3 here. And I'll tell you why here in just a second. But they're opposites, so they cancel each other out, leaving just the x equals log base 3, 7. And that's your answer. And you could type this into the calculator, and it would give you the decimal. It would tell you what that's equal to. Now, the notes later on, you'll see that they kind of have a different procedure to do that. I want you to think through it using this, what I just talked about. It'll make it a lot easier, I think. Okay? So I'm going to recap. If you have an exponential, to solve it, exponential equation, to solve it, you have to do the opposite, which is a logarithm. You got to do it to both sides. And it's going to be a log. This number down here needs to match this number right here. Since it's the opposite, it cancels out, leaving an x equals this. And you could type this into the calculator, and it'll tell you what that decimal is. Okay? And I'm going to tell you how to read a logarithm here in a second to give you an idea of what exactly that's saying. But let's continue down here. Big idea. Just as we can write rational numbers in decimal form and fraction form, so 0.5 equals 1/2, we can also write equations in exponential or logarithmic form. So go ahead and write that down. Exponential or logarithmic form. And that's what we just did, by the way. This was the exponential form. That right there was the exponential form. And I rewrote it in logarithmic form. Okay, so this was the exponential form. And I rewrote it in exponential form. And when I rewrote it in exponential form, that solved for my x. The notes, as you see, are going to skip that whole thought process. And they're just going to say, take this, turn it into this. But that doesn't give you any reason as to why you're doing that. Here, I gave you a reason as to why we're doing that. It's because it's the opposite. It's the opposite. It's the inverse. So again, exponential, you can rewrite it as a logarithm, just as we did right here. These forms create equivalent statements that represent the same claim. We did the same thing to both sides, so it never did change anything. So long as you do it to both sides, you're not going to change the value of the x. We are not changing the problem when we convert back and forth. We are simply rewriting the equation in equivalent form. So let's look at what the notes did. Like I said, I don't like how they presented this, but let's go ahead and look at it. It's saying b to the a equals c. The equivalent form is this. Log base b of c equals a. All right? It doesn't tell you why. It just says if you have this, you can rewrite it like this. But I'm going to appeal to the same logic that I used up here to try to understand what's going on there. So here's how I'm going to think through it. You have this being raised to the a equals c. And you remember up here, I was solving for the exponent. I'm also going to do the same thing here. I'm going to solve for that exponent. I need to get that a all by itself. Well, to do that, I have to use the opposite. Algebra is always about doing the opposite, doing the inverse. This is an exponential. The opposite of an exponential is a log. So I'm going to take a log of both sides. Log b to the a equals log c. I took the log of both sides. And just like up here, that number had to match this number, same thing here. What goes right there has to match this. So it's going to be log base b, b to the a, equals log base b, c. And since these are opposites, they cancel each other out. The log base b cancels out the b, leaving you just a equals log base b, c. And look, that's what they have right over here. They just didn't tell you how they get it. They just said, hey, if you have this, you can rewrite it like this. But I just went through the steps of why that works. Why can you do that? This is how you should think about it. You shouldn't just memorize that I can rewrite this as this, because there's no understanding there. And I mean, you'll get the right answer if you do it. But as you move into calculus and more advanced mathematics, you do want to think about that process that turns this into this. And it's all about doing the opposite. So if you're confused about any of that, please do rewind the video, watch that again, and try to follow the logic I just spoke of. Notation. I do encourage you to wait till we work some problems though before you rewind it, because as I work problems, it'll start making more sense. Notation. If the base of a log expression is 10, this is called the common logarithm, and it is written without a base. For example, log 3. You see how you don't see a number down here? If you do not see a number down here, it's understood to be a 10. So if you don't see a number down here after a log, it's understood to be a 10. So it's log base 10 of 3. And that's what that says. It's understood to be a 10. So it's going to be log base 10 of 3. If you just see log 3, it's the same thing as writing log base 10 of 3. So let's go ahead and work through example 1, parts A, B, C, and D. And the instructions say convert the following equations from exponential form. This is exponential form. You can see that all of them have exponents. Exponential form. Into logarithmic form. Okay, so we're going to do that conversion. And they want you to just do this. You're given this, I can rewrite it like this. But I want you to think through the logic of why it is, instead of just mechanically following this process step by step. I want you to think through this. So here it goes. If it didn't make sense up here, I'm gonna go over it again down here. All right. So we have 3 squared equals 9. 3 squared equals 9. I want to rewrite it as a logarithm. Well, if you have an equation, you have to do the same thing to both sides. So I'm going to take a log of both sides. I'm going to go log 3 squared equals log 9. And I know that what goes down here, the number that goes here, which is called the base, has to match the number being raised to the power. So this is log base 3, and this is log base 3. Logs and exponentials are opposites. So this cancels that out. Log base 3 cancels out 3, leaving just the 2. So these cancel out, and you get 2 equals log base 3, 9. And that's the answer. Those are equivalent. Writing this is equivalent to writing this. Okay? And you could have just followed this and rewrote it like this, and you would have got the exact same thing. But this shows you why. I'm doing the same thing to both sides of the equation. These are inverses, so they cancel out. Let's go ahead, do the same thing over here. I have 10 to the x equals y. I want to rewrite it in logarithmic form. Well, if I want to rewrite it in logarithmic form, I need to put a log in there. But I have to do it to both sides, because in algebra, we always have to do the same thing to both sides. So I'm going to go log 10 to the x equals log y, but I know that the base has to match this number. So this needs to be a 10 down here. That needs to be a 10. But you remember up here? If it's a 10, you don't have to write it. Log base 10 of 3 is the same thing as log 3. So I can actually leave this like that. That's fine. Or if I wanted to, I could put the 10 in there. I could go log 10 to the x equals log 10 y. They're inverses, so they cancel each other out. This cancels that out, and I get x equals log 10 y. Just remember this. If it's a 10 down here, if you have a 10 down there, you don't have to write it. So you could leave this 10 out and just go log y. Okay, let's move over to the next one. It's an exponential. We need to write it as a logarithm. Well, if I'm going to write it as a logarithm, I need to put a logarithm in there. But since it's an equation, I got to do it to both sides. Log RT equals log W. All I did was I took a log of both sides. But I know that this, whatever goes down here, needs to match whatever this is, whatever's being raised to the power. So it's going to be log base R, R to the T, equals log base RW. I know that logs and exponentials are opposites, so they cancel out. This cancels out, and I'm left with T equals log base R of W. And that's the answer. And finally, I go over here. I'm going to do the same thing. I'm going to rewrite the exponential as a logarithm. Well, if I'm going to rewrite it as a logarithm, there needs to be a log in there. But I need to take the log of both sides, because it's an equation. What I do to one side, I have to do the other side. So I'm going to go log y equals log e to the 3x. But I know that what goes down here and what goes down here has to match whatever's being raised to the power. E is being raised to the power. So I need to put an E down here and an E down here. Logs and exponentials are inverses, so the log base e cancels out the e. These cancel out, leaving a 3x equals log base ey. Now I'm going to tell you something. You'll almost never see it written this way, because this is a special logarithm. E, by the way, if you ever see e in math, it's not a variable. It's a number. It's actually a number. E equals 2.7, and it goes on forever without repeating. It's like pi. It's an irrational number. It goes on forever without repeating. Whenever you see log base e, you'll almost never see it written like that. Log base e is a special logarithm, and you write it like this. Ln. That's Ln, the natural logarithm. That's what it's called. Natural logarithm. Ln is just log base e. They're the same thing. Log base e is the natural log. So I'm going to replace it with Ln. Natural log y equals 3x. And there you go. You rewrote it as a logarithm. All right, let's go down to example 2. Example 2 says convert the following equations from log form to exponential form. I'm going to show you the quick way to do these, but the quick way bypasses the why. The quick way doesn't show you why we're doing it. Kind of like the notes up here didn't explain the why. The quick way I'm going to show you here, it bypasses why it works. So 2 of them I'm going to do the quick way. And then the last 2 I'm going to do in a manner that explains why it works. All right? So here's the quick way to do it that bypasses why it works. I have a logarithm. I want to rewrite it as an exponential. So it's the opposite of what we're doing here. Up here I had the exponential and I rewrote it as a logarithm. Here I have a logarithm and I'm going to rewrite it as an exponential. What you can do is you can always start with that number after the log. And you can go 7. Then what you do is you circle around and you pick that number up. That number that's after the equals, that's going to be the power. So it's going to be 7 squared. And then you circle around again, and that's what it's going to equal, x. 7 squared equals x. And you rewrote it as an exponential. Let's do it over here. Let's do our little shortcut. Start with what comes after the log, 3. You're going to raise it to this power, x. You're going to raise it to that power, x. And it's going to equal, you just go back around, y. 3 to the x equals y. And you rewrote the logarithm as an exponential. So yeah, you can always do that. You can do that circle around process. Start here. Start with this. That's the power. That's what it's equal to. Start here. That's the power. That's what it's equal to. That y. And the notes apparently want you to do that because they don't show you why it works. They don't show you why we're doing that. There's a few ways to look at it. I'm going to kind of dive into why we're doing this. Why does this circle around process work? One way to look at it is it has to do with how you read logarithms. It has to do with how you read logarithms. So look at this logarithm. I'm going to show you how to read a logarithm. Here's what a logarithm is saying. A logarithm, let me go ahead and erase these arrows. A logarithm is saying this, and this is really important because I want you to understand what the logarithm is actually saying. You start with this number, and a logarithm is saying, what power do I raise this number to get this? That's what it's saying. A logarithm is saying, what power do I raise that number to get this? That's all it's saying. That's what a logarithm's saying. And here, the power is 2. That's the power I raise 7 to get x. And that's what we wrote here. I'm raising 7 to 2 to get x. Because that's how you read a logarithm. That's what a logarithm is saying. That's what it means. So, right here, let's read the logarithm. The logarithm is saying, what power do I raise 3 to get y? What power do I raise 3 to get y? Well, this is the power, x. Okay, what power do I raise 3 to get y? X. So I raise 3 to the x to get the y. That's how you read a logarithm. Do notice that a logarithm is always equal to a power. A logarithm is always equal to a power. Because the logarithm, this side, is saying, what power do I raise this to get this? What power do I raise this to get this? Well, what it's equal to is that power. It's saying, hey, here's the power. This is the power you raise this to get this. This is the power you raise this to get that. So it's very important that you actually understand what a logarithm is saying. Let's go over here to C, and let's approach it in the same manner. First, I do not see a number down here, but that's not a problem, because remember above, we said if you don't see a number there, it's a 10. So that's actually going to be a 10 right there. And I'm going to read that logarithm. The logarithm is saying, what power do I raise 10 to get y? That's always what a logarithm is saying. What power do I raise the 10 to get y? Well, it tells me this is the power I raise it to. I raise 10 to the second power to get y. I raise 10 to the second power to get y. Okay? So instead of just saying, oh, we just loop around, now we're actually reading the logarithm the way it is supposed to be read. What power do I raise 10 to get y? It tells me 2. That's the power I raise it to. Let's do the same thing over here. I have ln, remember that's natural log. Natural log. Remember, natural log is the same thing as log base e. So I'm going to rewrite it as log base e. C equals 4. Let's read our logarithm. The logarithm is saying, what power do I raise e to get c? That's how you read them. What power do I raise e to get c? Well, it tells me this is the power. This is the power I raise e to get c. So I'm going to write that down. If I take e and raise it to the 4th power, it's going to give me c. And that's your answer. I rewrote the logarithm as an exponential. So please know how to read the logarithms. It's going to make things a lot easier. What power do I raise e to get c? It tells me 4. That's the power I raise e to get c. So I go ahead and write it down. E to the 4 equals c. There's another way to look at that, but I'm going to hold off until a future lesson to show you that. So I'm not throwing too much at you at one time. All right, let's keep on going. Evaluating expressions involving logarithms. Sometimes we can evaluate logarithms without the use of a calculator by utilizing its equivalent exponential form, which is what we're doing up here. Logarithm turned into an exponent, or an exponential. Evaluate the following expressions without a calculator, because you could just type them in. You could go to Desmos and you could type that in. You could go log base 2 of 8. You have to go into your functions on Desmos, and you'll see something that says log C, and then it'll allow you to type a number in down there. So yeah, you could just go log base 2 of 8. It'll tell you exactly what it is, but you don't need to do that on all logarithms. If it doesn't come out to a decimal, you can just figure it out. So let's look at this one. I'm going to think about what is the logarithm saying. I'm going to read that logarithm. 2 to what power gives me 8? That's how you read them. 2 to what power gives me 8? And I'm going to write that down. I don't know what power it is. Notice how it doesn't say equal. I don't know what the power is. Okay? If all these up here, like this one said equal to 4, I knew the power. It was 4. It told me. Here it doesn't tell me. So I'm going to call it x. I'm going to say 2 to the x equals 8. I don't know what the power is. 2 to what power gives me 8? I don't know. So I'm going to say x. 2 to a power I don't know gives me 8. 2 to the x equals 8. And then I'm going to break this down even more. You probably just look at that and you can say, well, 2 to the third power is 8. So it must be 3. But I'm going to break it down like this. 2 to the x equals, I'm going to rewrite 8 so it has the same base that you have over here. I have a 2 over here. So I'm going to see if I can rewrite 8 with a base of 2. 2 cubed. Okay? And now I can see 2 to the x equals 2 cubed. For these to be the exact same thing, the x has to be equal to 3. Because if it was equal to 3, then both sides are equal. So the x equals 3. And that's your answer. Don't lose sight of what it was saying. The original problem was saying 2 to what power gives me 8. Now I know. 3. That's the power. Let's go over here. Do the same thing. 5 to what power gives me 25? I don't know. It doesn't tell me. It doesn't say equal. It doesn't tell me what power it is. So I'm going to say 5 to what power x equals 25. And then I'm going to solve it. Well, this one you can just look at and you say, well, 5 squared x must equal 2. Okay, I know that x must be equal 2 to get 25. Let's go over to this one. Do the same thing. 2 to what power is 32? It doesn't tell me. It doesn't say equal some number. If it did, I would just say to that power. So I'm going to say 2 to what power equals 32? And I think about that, well, 2 to the third power is 8. 2 to the fourth power is 16. 2 to the fifth power is 32. So this must be 5. X equals 5. Okay. So again, to read it, this original logarithm was saying 2 to what power is 32? We just figured it out. 2 to the fifth power. Let's go over here and do this one. If I don't see a number after a logarithm, it's a 10. Unless it's a natural log, in which case it's an e. But if you don't see anything after a log, and it's not at ln, it's on natural log, then it's a 10. So I'm saying 10 to what power is 100? Well, I can just write that down. I know that it's 2. 2. And actually, I look back at these, I shouldn't have said x, because it didn't say, there was no x in this. It's just a number. So technically, probably should have put the x there, but it doesn't matter. You know, that's the power, that's the power, that's the power. And that's the power. 10 to the second power is 100. And then we keep on going. Let's do this one. I'm going to speed it up a little bit because I think you kind of see what I'm doing here. This one here. 16 to what power is 4? 16 to what power is 4? I'm going to write that down. 16 to what power is 4? 16 to what power is 4? This one, you might want to, you remember that step-by-step process I did up here? You might want to do that down here. So what I did right here was I got the same base on both sides. So I'm looking at a 16 and a 4, and I'm thinking, what number can I write to a power to give me both a 16 and a 4? That would be a 2. 2 to the 4. 2 raised to the 4, that's 16. That's 16. That's 16. The 16 is being raised to the x. That's 16. It's being raised to the x. So I'm going to raise that to the x. Equals, and 4 is 2 squared. So now I have the same base on both sides. That's what I want. Remember, when you have a power to the power, you multiply them. So this is going to be, I'm going to go down here. 2 to the 4x equals 2 squared. And now, let me show you how to solve this. You see how the base is the same? It's a 2 and a 2. That's what you want. Because if the base is the same, you can just ignore the base. And you can just say, well, it must be the case that 4x equals 2. And then you solve for x. X equals 2 divided by 4. Divide both sides by 4, which goes down to 1/2. So the answer here is 1/2. And that makes sense. 16 to what power gives you 4? 16 to the 1/2 power is 4. Because if I raise something to the 1/2 power, that's the same thing as the square root. And we mentioned that a while back. If I raise something to the 1/2 power, it's the same thing as taking the square root. Square root of 16 is 4. Okay, I'm going to go pretty quick through the rest of them. 3 to what power is 1? 3 to what power is 1? Well, 3 to the 0 power is 1. Anything raised to the 0 power is 1. So the answer must be 0. 3 to what power is 1? 3 to the 0 power is 1. Then I go over to my next one. If I don't see a number after the log, it's a 10. Unless you see an ln. ln, it's going to be an e. But if it's a log, it's a 10 if you don't see a number. So I'm saying 10 to what power is 10? 1. 10 raised to the 1 is 10. And then I go over here to this last one, and I'm saying 6 to what power is 1 over 36. So I'm going to write that down. 6 to what power is 1 over 36. I want to go over this one, make sure you understand what's going on here. You remember back here, I wanted the same base on both sides. Same thing here. I want the same base on both sides. So I'm going to look at this 6 and 36. I know that if I have 6 squared, that's 36. Okay? So I can actually have, this is the base, and I can rewrite the 36 as having a base of 6 as well. 6 squared. And then I have a 6 as a base on both sides. So I'm going to do that. I'm going to have 6. I'm going to carry it down here. 6 to the x equals 1 over, not 36, but rather 6 squared. See that? I just took the 36 and I made it 6 squared. And now I have a base of 6 on both sides. And that's what I want. I want the base to be the same on both sides. Now, notice how the 6 is in the bottom here, but it's on the top here. I need to get this out of the bottom so it can match this side. And I can do that. I can bring it to the top. But whenever I bring it to the top, the exponent becomes its opposite. So if I bring this to the top, it'll no longer be 6 squared. It'll be 6 to the negative 2. Okay, so I'm going to bring it to the top. 6 to the x equals 6 to the negative 2. And then, since these are the same, I can ignore them. I can just ignore those, and I can say that x equals negative 2. And that's the answer, negative 2. So 6 to what power is 1 over 36? 6 to the negative 2 power is 1 over 36. So if there's anything you didn't understand there, please go ahead and rewind that video and follow that explanation again. Let's go down to example 4. Example 4 is easy because it says use a calculator. Type them straight in. Go to Desmos. Type log 9. You can actually type log 9. If you don't see a number down here, you know it's a 10. You don't have to put the number. If you don't see a number, you don't have to put it. Just go log 9. You can actually go onto the keyboard and go log 9. And it'll give you that answer. It'll tell you what power do I raise 10 to get 9. Same thing over here. This one's saying what power do I raise 10 to get 6,125. Well, you just type it straight into the calculator. Straight into the calculator. LOG 6125. Then go over to this one. Well, here you have to put that 2. I'm going to pull up Desmos real quick to remind myself where those are located. So to type this 2, go to Desmos, go to Functions, and go to Calculus. Oddly enough, they put it in the Calculus functions. It's really not calculus, but that's where it's located. And you'll see a log A. Go ahead and click on that. When you click on the log A, you'll be able to type that 2 down there. And then you just type that in there, and it will tell you the answer. It'll tell you what power do I raise 2 to get 10. And then do the same thing here. Type it in, use log A, type in the 7, and it'll tell you what power I raise 7 to get 135. Okay? So just use your calculator to get those answers. And let's keep on going. I'm thinking of whether or not I want to talk about. I would definitely want to talk about this, but to talk about it right now, it's kind of a long video, and this is going to make it even longer. This is not complex. It'll take me about 10 minutes on Monday to explain what's happening here. So what I want you to do on the worksheets, if you ever get to something that's talking about a logarithmic scale, skip it. Okay, if it's talking about a logarithmic scale on the worksheets, skip it. We'll talk about it on Monday. Just do problems that look like the stuff we did all the way up here. Do problems that look like this. If it says logarithmic scale, skip it. We'll talk about it on Monday. Won't take long, take probably about 10-15 minutes, but I just think this video is getting too long, and I think it's best just to hold off on that. So again, on the worksheets, don't do the logarithmic scale problems. We'll wait till Monday. And there are worksheets. I think there's only one worksheet, if I'm not mistaken. I believe there's just one in this unit, this lesson. So that's the homework. Do that worksheet, skip the logarithmic scale problems. All right, take care, have a good weekend, and I will see you on Monday.